Okay, so let's have a look at this. This is the bit that always scares me, that I'll forget how to program CUDA in front of the class. It's the classic fear. Okay, so I think somebody had an error before with the cuinit. So here, the first to-do we have is it's asking us to implement a CUDA kernel, and it's been kind enough to give us the template for it. I am going to, the first thing I have to do is say I'm writing a CUDA kernel. Now, the next thing I have to do is I need to get the index, so I can type in int I equals thread idx.x, and then, okay, I've got my demo of what I want to do up here. So why don't I just cut and paste that? So y equals y plus alpha times x. Let's do some shorthand there. That's the same thing. Okay, so that is our kernel. Then when we go down to the next to-do, so the first to-do here says calculate the grid dimensions, and then there's a comment here saying ignore for the first kernel writing exercise. So ignore it. Don't worry about that. We'll do that in a moment. Then we need to launch our kernel, which was Axby, right? Axby, triple chevron syntax. I can never remember what this looks like. Okay, I need the n, the alpha, which is 2.0. I need a double pointer to x, and that's going to be x on the device. Yeah. Everything else should have been written for me. Now you might notice that you might wonder, why is he using, malloc on the device and CUDA memcopy and all of this when you could just be using managed memory? And the answer is, I want to be able to run this and do a little bit of timing and have a look at things. And if we're using managed memory, the timings aren't so reliable. So we need to tell, okay, we're going to launch a GPU kernel. We need to say how many threads, what sort of configuration it's to have. And that was 1, a comma, n. So I have n threads. Now let me just check, is it n? Yes, it's n. Okay, so. Axby.cu, line number 12. So line number 12, oh, okay, I stuck. Okay, did everybody manage to get to this stage? Okay, so I'm going to do the templated version right now. So for those who like C++, okay, so this would work if I passed in an array of integers or floats or whatever. Great, so let's run it. So I have to allocate again. Invalid configuration argument. Oh, of course. So I tried to run it with a very large value, and I got an invalid configuration argument. Let's do what I actually suggested we do. Okay, so it's telling me, it's got some timings here, how long it took to copy from host to device, and how long it copied from device to host, and then how long the actual operation of adding the vectors together took, and then the total time. And some extra statistics. Okay, if we know how long it took and how much information data we copied, we can calculate what the bandwidth was. So let's run that with 9. Let's go up to 10, which will be 1024. So you can see that as the size of the problem gets bigger, the amount of memory bandwidth we're getting is also increasing. It's not exactly the 11 gigabytes a second we were promised, but you'll find that if you want to get 11 gigabytes a second, then you're going to need to start copying bigger chunks of data. So with arrays of length 1024, we're going to have 8 kilobytes getting copied each time, which isn't much. So what if I go up to 2048? Invalid configuration argument. So what does this show us? Anybody? Yeah, the most number of threads we can use by deduction. Well, we haven't tried 1025 threads, but let's assume that 1024 is the maximum, because these things usually work in powers of 2. So if we have more than 1024, it breaks, but that's 1024, that's a very short vector. There's no reason to be using a GPU to do that. So if you wanted to extend the kernel to work for larger arrays, if anybody tried to implement that, the basic idea you say is, well, instead of having one thread process one input item, if I've got n is equal to something, and I know that I've got 1024 threads, and n is bigger than 1024, I'm going to have to get each thread to process multiple items. So you would have to have a little for loop inside the kernel. And I will leave that as a famous exercise for the reader to work on. So the next part is, so we're scaling up, working with thread blocks, because 1024 isn't many parallel work items. I've just told you that there's 3,582 CUDA cores on a GPU. We're not even touching that. It's hardly massively parallel. And this comes back to what was that number 1? When we launched the kernel before, we had 1, a comma, number of threads. And this is where this comes in. So in this XP exercise, we're limited to 1,024 threads, but we want to go much beyond this. We want to have millions, even billions of threads launched to really start taking advantage of the GPU. So how do we do that? Well, there's this idea called thread blocks and grids. So kernels are executed in groups of threads called a thread block. And in the launch configuration before, we had 2 arguments. The first argument we were setting to 1, and the second argument we were setting to the number of threads that we wanted. So this second argument is actually the dimension of how many threads we want in a thread block. And then this first argument is the total number of thread blocks we want. So when you launch your kernel, you create blocks with a certain number of threads in them, and then you create as many of these blocks as you need to do all the work. And this group of blocks together is called a grid. So this is going to launch a grid of grid dim blocks. So this tells you how many blocks, thread blocks, we want to execute. And then each block has block dim threads. So now that we look at this, we say, aha, okay, the most threads that we can have in a thread block is 1024. So if we want to process a bigger array, we're going to have, let's say we wanted to process 2048, an array of length 2048, we're going to have to launch a grid with 2 thread blocks, each thread block with 1024 threads in it, for example. So previously we just defaulted to this value being 1, but now we're going to think about how do we increase that value. And why do we have this additional complexity? Because wouldn't it just be easy if we could just say, give me 1,000,000 threads and have it all go off and do the work? And the reason is that it's to do with the underlying hardware, because when you're working with threads, they need to be able to coordinate and work together at points. So the algorithm we're working on at the moment, there isn't an awful lot of need for coordination. Well, there is a lot of coordination, but there's not much need for sharing of information. But we'll see the moment you start trying to do more interesting kernels, you're going to need to have synchronization. Let's say we're all a bunch of threads in a thread block do some work together, and then they all have to stop and synchronize and make sure that they wait for everybody else to finish before proceeding to the next step. So we do need some sort of synchronization and sharing of resources. And unfortunately, this sort of synchronization doesn't scale past a certain number of cores or threads. So you can do synchronization for 32 threads, or 64, or 1024, but at a certain point, the overheads, because there are overheads associated with synchronization and getting threads to work together, those overheads become too great. So on the P100 GPU, we saw it before. I'm just going to use this picture here actually. We saw before that when we looked at this big picture of the GPU, it had all of these little green squares, and each of these green squares was basically one of these blocks here. So this has got 64 CUDA cores in it, and a little bit of shared memory. That is some shared resources that threads that are working together can use to share intermediate results that they're working on. So, and each P100 GPU has got these SMXs, and it's got 56 of them with 64 CUDA cores, and they can run a maximum of 2,028 CUDA threads at the same time. They can run multiple blocks. And threads within a thread block, they run on the same SMX. So that this means that they get shared resources and they have full thread cooperation. So the threads that are running inside a thread block on the same SMX, they can synchronize with one another, they can share information with one another, and they can work together. But we couldn't do this for a whole GPU with all the threads. We couldn't do this efficiently with that many CUDA cores. So basically, they break the processor up into chunks, into these SMX chunks, on which you have cores that can work together. So the work is then broken up into blocks, which we distribute over the SMXs. So we've got 56 SMXs on the GPU, but we have 56 SMXs, but the sorts of typical workloads we want to run where we actually saturate the GPU and get lots of work out of it, we're going to want much more than just 56 thread blocks or 100 thread blocks. We're going to launch typically stuff that has got thousands, tens of thousands of thread blocks in it. So how do we launch, when we launch a kernel, how do we launch that many that many blocks of threads when we don't have that many SMXs to run all the thread blocks? And this is all looked after behind the scenes for you. But the GPU basically breaks up the work into these thread blocks and runs as many of them at the same time as it can and keeps all the rest waiting in a queue. Then as each one of these thread blocks finishes its work, another one gets popped onto the appropriate SMX, and the hardware and software runtime look after managing all this stuff for you. So just to reiterate these ideas with a picture, we start with the idea of a thread, where a single thread is running on a single CUDA core. We group these threads together into a block, into a thread block, and the block is executed entirely on one SMX. And if we have enough resources on the SMX, we can put multiple blocks on the same SMX. What do I mean by if we have enough resources? Well, we're going to learn about shared memory later, which I've got down here as this little yellow area. So shared memory is a scratch pad memory that threads can write into, so they can all kind of write values into that, then other threads can read this and they can use this to coordinate amongst them, to transfer information amongst themselves. Depending on how much shared memory your kernel uses, if your kernel uses lots of shared memory, then you might only be able to fit one thread block on an SMX. But if it doesn't use any shared memory, then you might be able to fit more onto the SMX. Shared memory isn't the only resource. There's also the register file and other resources that are shared. But this gets looked after for you automatically. So we start with a thread. Then we have a thread block which runs on a single SMX. And then we have a grid of thread blocks which may or may not be distributed over multiple SMXs. And so we execute our kernel on a grid of blocks, and it's important to note that we can have multiple kernels running at the same time. So if your kernel that you've launched is only using half of the SMXs, or half the resources on the SMXs on the GPU, and you've got another kernel that you've said can run at the same time, the runtime will do its best, will attempt to execute both kernels at the same time on the GPU. And now and we're going to come back to this later on, but a key point to understand here is that threads that are in the same block can synchronize and share information together. And we're going to learn all about that tomorrow. However, threads that are not in the same thread block, there are some limited ways that they can exchange information, but they definitely don't have access to the same shared memory or some of the same shared resources, and you don't have any control over which order thread blocks get run. So you can't make the assumption that threads numbered 0 to 32 are going to run before threads numbered 1 million to 1,032,000. You can't make any assumptions about which order they're going to be run in or which one's going to finish first. So that's kind of a classic, that's a tricky thing to understand, but you can't rely on synchronization between the SMXs, between thread blocks so much. So before calculating the thread index, the I, was pretty simple. We just read the thread idx.x value and used it. But now we're working with multiple blocks. We need some more information, which is available from the following magic variables. So we had just one magic variable before this thread idx. Now if we're going to figure out where we sit in this grid, we're going to need some extra information. So thread idx down here, thread idx is the index of this thread inside its thread block. Block idx is the index, is an identifier for which thread block we're running in. Block dim is the number of threads in each thread block, and grid dim is the total number of blocks in the grid. So you can put all this information together to calculate, let's say, to calculate what index or what your work item is. So here's a simple little example. We have launched 24 threads, and we've launched them in thread blocks of size 8. Now this isn't a realistic launch configuration. You should have at least 32 threads in a thread block, but this is just for demonstration purposes. So 24 threads with 8 threads per block. That means block dim.x is equal to 8, because block dim, remember, is the number of threads in a block. So that's equal to 8, because we have 8 threads per block. And grid dim.x is 3. So we've got 3 thread blocks. So to calculate the index of an individual thread, we use this little bit of arithmetic here, that the index is equal to the thread idx, that is the index inside this thread block, plus the location of the first thread in the thread block. So an example of this one here is, let's say we want to get this value. What thread am I here? I am the fifth thread in the second thread block. Well, to get that value, it's going to be 5 plus 8 times 1. and that's going to get us 13. Because remember, they're numbered, everything is numbered from 0. So the second thread block will have index 1. So all of these threads here in this block, they will have block index.x is equal to 0, 1, and 2. And that's how you calculate the offset inside the inside your thread block and your global index. Any questions?
Yeah, can we go 2 slides back to this?
Yeah. This?
Yeah.
Oh, yeah.
Good. So I'm not 100% sure whether I understand it correctly. So say I execute this kernel with grid dimension 1 and 1 thread. Then I have the example from the top, I guess.
Yeah.
If I have grid dimension 1 and 64 threads, I guess I have the second one.
Yeah. Also, if you have grid dimension 1 and 128 threads or 512 threads,
yeah,
you still have this one here.
Okay, that means
so,
in this case, all the threads get not executed at the same time.
Yep. So this is what I was in the introduction slides. It's a good question, because in the introduction slides, I showed this diagram about how does the GPU hide latency? How does it do this? And the way it does this is by saying, okay, I've got 64 cores here that can be executing instructions, but I need to have more, I've got to have multiple threads per core. So one set of threads will issue an instruction. And then whilst we wait for, let's say, the memory access or whatever resource is required for that thread to do the next step, we quickly do a context switch, set in another set of threads that will then issue their instructions. So that's why we might have a thread block with, let's say, 128 or 512 threads, which is more threads than we have cores. But we need that because we need to have multiple threads that we can schedule so that they can do this latency hiding. And how many threads you need? Because what's the ideal number of threads to put in a thread block? And the answer is, I've actually got a slide about that, is, well, that depends on the nature of the computation you're doing. And I think Peter Mesmer tomorrow is going to go into a lot more detail about how to make that decision. But then at some point, if you order multiple thread blocks, they're going to get distributed over multiple SMXs.
The grid, so the number of blocks I can have is also arbitrary. It's not limited to the number of SMX. I can have more and then they get...
Yes, it's much more. It's 2 to the power 32, I think. It's effectively infinite. Yeah. It used to be 65,000, which was really annoying, but it hasn't been that way for a long time. So yeah, you can have many more thread blocks than there are resources on the GPU, and the GPU basically just, whenever a thread block has finished executing, when that computational resource becomes free, it will schedule the next thread block immediately to start processing. So the thread index calculation, do we have any questions about that? Okay, so that's how we calculate the index inside here. And now we're going to answer that question about why do you pass n as an argument when you don't really need it, because you calculate your index here. And the answer for that is, well, now that we're launching multiple thread blocks, we're going to end up, we can end up in a situation where, let's say we want to process 700 values, or yeah, we want to have 700 threads, but we're using thread blocks of size 512. That means we're going to need 2 thread blocks, but in the second thread block, the last thread block, only some of the threads are going to be working, because we've got 700, 512. So you've got quite a few of the thread blocks are going to have to be idle. So the first thing we want to do is figure out how many thread blocks do we need. And this is how we calculate. So first of all, we figure out what our block size is. So here we're going to set the block size to be 512. And then we calculate the number of blocks. Now the number of blocks isn't just n, the number of threads we want, divided by the number of threads per block, because we're using C here, or C++, so when you do division with integers, it always rounds towards 0. So in that case, if you have a remainder, so if we did 700 threads divided by 512, we would end up with 1 being the answer. But we don't want 1 thread block, we want 2 thread blocks. So we have to handle the case of if there's not a perfect, if the number of threads we want is not perfectly divided by the block size. And here's my favorite way of doing that. We go n plus block size minus 1 divided by block size. And that's always guaranteed to give you the right number of blocks. Because if n is if block size is a factor of n, then if you're adding block size minus 1, will be 1 less than the next multiple of block size. So when you divide by block size, you're just going to get the right number. But if it's 1 bigger, if it's any bigger than a perfect multiple, then we're going to get this extra value, this extra 1 added on. You can convince yourself with pen and paper pretty easily. So now we call our kernel with the number of blocks and the block size, A, B, and N. But now we've got a situation where we're now creating more threads than we actually have work items to do. So we need to calculate what our index is. This here, I is equal to thread IDX plus the block IDX times block dim. And then we have to have an if guard here. Only actually do the computation if I is less than n. So that's why we need n. And this might look a little bit inefficient. Now we've got an if statement in here, but it's actually very efficient, and this is handled very, very efficiently on the GPU. So okay, this is exactly what I said before. So calculating the grid dimensions, we have to use this formula here. You can use slightly more complicated ones if you want to, but this is a nice shorthand. So I think I've said everything there. Any questions? Yes.
So in this situation, let's say that n is 700. Would it be better to try to evenly divide to set, for instance, a block size, a smaller block size, so that you have it?
No, not really. I mean, so n equals 700 with block sizes of size 512 is kind of a trivial example. It's not a very good one. Normally, we're going to be deciding between having, a much bigger number of thread blocks, 100,000 versus 100,001 thread blocks. So where it doesn't matter too much, yeah. So yeah, that was a very trivially small example. This is the problem with talking about this stuff, is you want to have nice small examples you can draw on the board, but at the same time, you usually run with much larger configurations. Yeah.
Here in your kernel, you do just one element of the form of for loop, so one I.
Yep.
Could you also chunk the?
Chunk the.
10.
Okay, so the question is, in this kernel here, we're just having one thread processing one item. The question is, can we chunk the work? And the answer is yes.
Is it more efficient?
Depends. In this case, yes, you probably can get. I've not played around with it. I suspect here you probably could. It really does depend. There are some kernels definitely where you want to have multiple work, where you can kind of hide memory latency by issuing a load, then doing a calculation, load calculation, load calculation. Or where if you're using shared memory to do something, it's much more efficient to fill up the shared memory with multiple values per thread and then have them all work together than it is. But so the answer is yes, you can do that. You can write an awful lot of, you can do an awful lot of things in a kernel, but exactly what the best approach is really depends on what you're doing. Okay, so the next question is, well, how many threads per block? Do I use 1024 because that's the most, or do I use 64 or 128? And the answer, so the short answer is use 128 on the P100. It seems to be, and a guy from NVIDIA also told me this, 128 is the short answer. But then you can always experiment by hand. You know, you can try, well, how does it look if I use 96 or 64 or 256? The long answer is how many threads is a good number of threads really depends on the kernel that you've got. How much resources it's using, what's its ratio of compute to memory bandwidth, and I don't go into that in too much detail, but tomorrow we're going to have Peter Mesmer from NVIDIA is going to be here to have a bit more of a deep dive into the P100, and he's going to talk in more detail about exactly how the SMX works at a lower level and give some information which might help understand, you know, how many threads you want to use. But by default, if you're just playing around, I would start with 128 and then experiment. So we now have the next set of exercises. So these exercises are basically to start off with taking our little AXPI kernel that we wrote before and extending it so it works for arbitrarily large value of n, which will require updating the kernel, then updating the call site, also calculating the grid dimension, and then testing it. Then we've got a little, and I would like you to do some testing where you start with some small arrays of length, you know, 1024 and then 2048, and just keep doubling it and have a look at how long it takes and just see if you can notice any trend. You should notice something pretty interesting. And then once you've done that, there is another example called Newton.cu, which has got some work for you to do. You can finish off there, and then you can have a look at how the kernel timings, and specifically have a look at how the timings for the memory transfers and the kernel timings compare to those for the AXPI example. And then if you get to the last couple, just ask me, and we can have a look. The last one we have an AXPI OMP, which is an OpenMP implementation. So you can try to compare how fast OpenMP is versus CUDA. So compare one of our Intel processors with 12 cores to one of our CUDA processors, GPUs. And also, if you want to, you can experiment with the block size, 64, 128, 256. Okay, so I've got some results that I want to show just related to that question before. So I was talking about OpenMP before, which is a set of compiler directives where you can annotate your source code and the compiler will generate multi-threaded code for you. So we have a version of this AXPI, which is implemented using OpenMP. And I did a benchmark where I compared the OpenMP to the GPU. That took quite a long time because for small values of n, I wanted to use one OpenMP thread, and then for larger values, I wanted to use more OpenMP threads. But I tested this on an 18-core Broadwell processor, so basically the biggest, beefiest Intel processor you can get, versus P100 GPU. And the black line here is basically the normalized time taken by the OpenMP, so it's 1 all the way along. So now we're basically seeing, for a given value of n, where this is, this means 2 to the power of 20 here. For a given value of n, how much faster was the CUDA version than the OpenMP version? And you can see that for smaller values of n, the GPU is slower. And at about 2 to the 14, the GPU started to get faster. However, it wasn't until we got to about 2 to the power of 21 that we see the full 7 times speed up. And I would actually hope to see a bit more speed up because we've got more than 7 times as much floating point performance and more than 7 times as much bandwidth on these P100 GPUs than we do on the CPU I was working on. But I haven't had time to look into why that is. But the point is, if you want to get the full speed up, you've got to have quite a lot of parallel work to do. And also remember that typically these server processors, they come two in a node. Normally we'll have two of them in a node, whereas with the GPU we have one CPU and one GPU. So you should probably divide this speed up by 2 if you wanted to get like the actual normalized performance node to node. But still, so the GPU definitely comes out, it's faster. But it's with a caveat, you know. You're only going to get this nice 7 times or 3.5 times speed up when you normalize it if you have large enough data sets and if you're working at a big enough scale to actually utilize all the resources on a GPU.